Hello. We are going to be analysing and solving non-linear ordinary differential equations, or certainly ones that are reducible to linear form in this presentation. And I've already written one down in equation 1 here. And we're going to look at, first of all, why this equation is non-linear. And as I've written here, a non-linear ordinary differential equation is formed by the product of the unknown function y, so we've got a y term here, and its derivatives, for example, in this case, d squared y by dx squared. And here we have a product of y's own derivative with y's own derivative, so it's a derivative squared. So all of these factors mean that this equation is non-linear, but we have to, in order to solve it, we have to try and linearize it, at least put it into linear form. So how are we going to do this? Let me just go back to this equation here. You can see we've got a squared term here, dy by dx, which looks as though it's complicated the situation. And sure enough, in its present form, it is quite complicated. But in actual fact, when you have derivative terms squared like this, you can actually substitute, not in all cases, but in some of the more simpler cases, you can substitute a kind of another variable in for dy by dx, like u or v, p or q. And in this case, I'm going to substitute dy. I'm going to substitute for dy by dx the variable u. So you can see in equation 1, you would end up with something like, well, just forget about this term that's underlined in yellow, but you'd have something that's minus u squared. Of course, we have to simplify the far left-hand side of this equation 1 here, because we've still got a y, a d squared y, and a dx squared there. So first of all, what we do is we differentiate dy by dx again, so that we get d squared y by dx squared equal to du by dx. Now, why have I done that? Well, we've got a d squared y by dx squared term here, and I knew to do that because we have a d squared y dx squared term here. Let's write that in red, if I can do that. So this term is d squared y by dx squared there. So that's why I differentiated what we had with respect to x once again, so that we get a term for du by dx being equal to d squared y by dx squared. Now, because we've got a y times a second derivative of y with respect to x, if we substitute that back into equation 1, the problem there is, as it stands, that we end up with 3 variables in the equation, and we don't want 3 variables. So what we do is we use the chain rule, and we split this up into du times du over something, I'll just call that question mark at the moment, times question mark over dx. Okay, so what are we going to choose for the question mark? Well, as you can see, it's got to be y, because we've got a y coefficient here. We don't want any third terms that would make it difficult or impossible to solve this equation. So we're going to be solving it in terms of y. So I'm going to write a dy there and a dy there. And from this part of the equation here, you can see we've got dy by dx is equal to u. And of course, we've got a dy by dx term here. So we can quite simply write this as u times du by dx. So d squared y by dx squared is equal to u du by dx. So let me just write, I think we need to write this equation, the equation 1 down again, so that we've got something, we've got a good reference point. U squared equals 0. So we know that this is equation 1 as at the beginning of the presentation. Right, okay. So we've got d squared y by dx squared equal to u du by dx. So we can just substitute that in. So we get y times, let me make that, there we are. So we got y times u du by dx minus u squared, and that's equal to 0. By the way, I should have really written that u as dy by dx all squared. I was getting ahead of myself there, which was not very clever. So you can see we've substituted in the term for d squared y by dx squared and the term for dy by dx to get this. And now it's a lot easier to solve. So what we can do is you recognise there's a u and a u squared term here. So there's a u there and a u squared term there, which means that we can factor out one of the u's, and we rewrite this as u times, in brackets, y du by dx minus u equal to 0. And straight away you can see from that that u has to be equal to 0, or this has to be equal to 0. In actual fact, we can write u, and we know that u is equal to dy by dx, and that's equal to 0. So if we integrate the dy by dx term here equal to 0, what we end up with is a very basic special case solution, which is y equal to c1. As I said, this is a special case of the general solution that we will eventually get from solving this term here, this part of the equation here. So let's crack ahead and now solve this part of the ordinary differential equation. So we've got y du, oh, excuse me, let's just eliminate that, y du by dy. I hope that's right. Let me just check it. Oh, have I made a mistake somewhere? Let me have a look. I have made a mistake. This term here should be a y, and that should be a y. So we've got y and y. Okay, sorry about that. So we've got y du by dy minus u equal to 0. And now we've got a differential equation that is linear and much easier to solve. And I'm just going on to the next page. So I'll write this down again. Y du by dy. Well, actually, I'm going to take the u to the other side. So it was y du by dy minus u equals 0. Now it's become y du by dy equal to u. This is separable. So we can bring all the u's onto one side. Don't forget to put the integral sign in. And that is equal to the integral of dy over y. And if we integrate, what we find is that we get the logarithm of, I'm going to put modulus signs in there, which is what some mathematicians do, and that's equal to the log of y plus, I'm just going to call this a as a constant, because I want to use c's as the main constants. That can be written as log of y, sorry, making mistakes again, let's just rub all that out, erase all of that. And so we've got log of u, actually it is a log of y, isn't it? So log of u is equal to log of y plus the log of, we'll just call it c2. Okay, a is, you can just write a as the logarithm of some other constant. It doesn't matter. It's perfectly possible to do that. So we've now got the log of u equal to the log, and by the law of logarithms we can multiply this y and this c together to get c2y inside the arguments of the logarithm, which means that we have u, oops, there's a bit of a y there. So we've got u equal to c2y, okay? But we're not finished. We're almost there. We've got a relationship between u and y. But what is u? Well, we know what u is. U is dy by dx, and that is equal to c2y, which means, if I just write it over here, if we separate the variables out again, we've got dy over y, the integral of, equal to c2 integral of dx. Well, that's fairly easy to solve, I hope. So what is the integral of dy divided by y? Well, that is just the log of, let's make that look a little bit clearer. So we've got the log of y equal to c2x plus c3, okay? This can be rewritten by taking the exponentials of both sides. So this is e to the c2x plus c3, which is the same as writing e to the c2x times e, whoops, just erase that and make it a little bit neater. So times e to the c3, which is, I should have called that c something else, but we'll call it c4 times e to the c2 x. Okay, right. So we've got a final solution to the original ordinary differential equation, which is that y equals some constant times e to another constant times x. Okay. Well, please tune in to watch my next video, because I'll be explaining how to solve another type of non-linear ordinary differential equation. So see you then.